In general, microprocessor performs multiple tasks at a time with the help of user program or user-defined program at a time. So in a top-down manner, microprocessor executes the program which are stored in the memory. It accesses the memory, reads instruction, executes tasks, and performs so many more functions. So once the microprocessor is in a state of executing the program, so there is in general no way to interact or interrupt this process. But there is a systems, and every microprocessor will receive a signal from the external world or external device. There is a hardware architecture, inbuilt hardware architecture inside its internal architecture. So what will happen and what is the interrupt process? So interrupt is a process where an external device can get the attention of the microprocessor. And this process starts from the connected I/O device. In order to communicate with the microprocessor, so a different microprocessor, it may provide a means to interrupt the program of a microprocessor. So there are different methods of interrupt, that is polling method and interrupt method for data transfer between the I/O devices and the microprocessor from its memory. Now I will discuss a polling method later, but what is interrupt method? Interrupt is a signal sent by the external device to the microprocessor to request the processor to perform a particular task or work. It is a simple routine program that keeps a check of the occurrence of the interrupt. Mainly in the microprocessor-based system, the interrupts are used for data transfer between the peripheral I/O and the microprocessor. That is the memory connected to the microprocessor. So this is one important task or example of the interrupt. If the microprocessor accepts the interrupt, it must send an interrupt acknowledge signal, because the 8085, if we notice, there is a two signal. One is called the INTR and INTA bar. INTR is called the interrupt request signal, which may arise from the external peripheral device, and upon receiving this interrupt signal, CPU, whatever may be its state of action, it immediately sends a interrupt acknowledge signals, that is active low, through this pin, that is in case of 8085. When the interrupt is received, the microprocessor suspends its current activity, means whatever may be the programming states, because microprocessor cannot go on idle. It always executes the program, fetch the instruction, execute the program, and this will go on repeated manner. So what will happen when it receives the interrupt signal from the peripheral device to its associated connected pin, microprocessor will suspend this program execution for the time being. It sends the interrupt acknowledge signals, and it will go to a specific memory locations, which is called that memory location may be supplied by the interrupt controller or may be fixed in case of the different interrupt systems. The processor executes the interrupt service routine or ISR, which is a kind of the subroutine, but this subroutine is not a general subroutine, but it is initiated by the interrupt request signal, and this ISR have a fixed starting address, and the program counter will load it automatically this ISR address. That is the beginning of the interrupt service routine or subroutine. Upon completing the tasks under the interrupt service routine, when it encounters the iReturn instruction, iReturn, which means the end of the interrupt service program, it immediately branches to the location where it has been interrupted. It is just like a subroutine calling. So that's why the stack pointer will be operating in a similar manner as it is observed in case of a calling the subroutine. So advantage is that the microprocessor did not waste time. That means during the data transfer between the external device and its internal memory, because microprocessor can give attention to these internal programs, and then when the interrupt will occur, with the help of the interrupt request signals, microprocessor will suspend the execution of the main program and it immediately give attention to a fixed task, that is programmable task, under the which are set aside in the interrupt service routine ISR. Again, after returning to that means when the program counter will updated with the return address, it will start executing the instructions in a normal way. So that is called the interrupt process for a microprocessor. Every microprocessor, there is an interrupt process which is described by the flow chart or flow diagram. So main program execution sequence is like that. The microprocessor will check the status of the interrupt request signal internally. If the interrupt has occurred, it will suspend the mainline program and it will invoke the ISR associated with that interrupt. So after finishing, again this will go to fetch the instructions from the main programs. And this is the start of the right hand side is a flow diagram of the interrupt service subroutine. So the microprocessor give attention only when it checks, that means the trueness of this interrupt signal, interrupt request signal. Yes. So automatically here, this part is written here, or this part is. So there are two flowcharts. One for ISR, which is called the ISR execution sequence. Another is called the mainline program interrupt sequence. So again, there are different types of the interrupt for the microprocessor. In case of a 8085, there are different types of the microprocessor, which are divided into two types. One is called the software interrupt, another is called the hardware interrupt. Now, hardware interrupts are truly the physical interrupt request signal which will occur over this respective pin, a specific pin of 8085. The names of the interrupt signals are called the trap, RST, which stands for the restart, RST 7.5, RST 6.5, RST 5.5, as well as a additional interrupt signal which are coming from the interrupt controller, INTR. So there are 5 kinds of the hardware interrupt, and there are so many software interrupt. And how the software interrupt will be initiated with the help of the software code. The codes are like that. That means, and these other except INTR, trap, RST 7.5, RST 6.5, RST 5.5 are called the vector interrupt. Vector interrupt. Why? Because they have a fixed starting address associated with the ISR. That means ISR will start from a fixed address. How the address will be calculated? Then method is like that. For example, there are 8 software interrupts available. For software interrupt, there are 8 software interrupts. The instruction code lies from RST 0 to RST 7. So for RST 0, the interrupt number, the formula is the interrupt number multiplied by 8, which is called the vector address in 16-bit. For example, RST 5.5, this number, the 5.5 number must be multiplied by 8 in decimal, which gives 40, and in hexadecimal it will be 28. So the 0028 will be the beginning of this vector address, the vector interrupt signal RST 5.5. So vector address for the RST 5, which is a software interrupt, because RST 5 is not a hardware interrupt, it is a software interrupt which falls in this line. The vector address is 28. Vector address for the RST 5 is 5 into 40, 5 into 8, which will be 40 in decimal. So that is 28. But for 5.5, it will not be a 40, you can calculate. So program counter will be loaded by the vector address as calculated using this formula. This instruction allows the transfer of program. That means whenever a single opcode RST027 is executed, the program counter will be forcibly loaded with the vector address calculated according to this now formula. So this instruction, once the program counter will be loaded to this address, what will happen? The CPU will automatically branch to this 28. There is no necessary to write the call the subroutine because it is a inter-service subroutine or inter-service routine. So same thing, that is inter-processing is done with the help of this first the generation of the vector address, and branching will occur by the updations of the program counter. But what will happen? The current content of the program counter that will be saved to the stack memory, obviously, because it is a subroutine. And according to the theory of subroutine calling, the content of the program counter must be saved before it will be uploaded, updated to the new value, that is 28. So these are the vector address for the software interrupt, each software interrupt, the opcode, corresponding opcode in hexadecimal is C7 to FF. So this is a valid opcode for software interrupts. But these are all vector address, but not initiated by the occurrence of any external signal, as because there are no pin corresponding to this signal. It will be initiated by the program code, that is software, and the vector address is like that. But interrupt, which is purely a interrupt, physical interrupt or hardware interrupt, and this will be initiated by the occurrence of a particular signal. What is that signal? That is a pin pin function name is trap, pin number 6, RST 7.5, RST 6.5, and RST 5.5, as well as INTR. So the hardware vector address, these are called the hardware vector address, are truly 1, 2, 3, 4. But this is not a vector address because the ISR code must be supplied by the external device called interrupt controller. But for this interrupt, vector interrupt, the address will be automatically determined using the formula as above. So this is the method of interrupt processing, and these are summarized in steps. Interrupt is caused by sending a signal on one of the interrupt pins. These are any one of the interrupt pins at a time or at a different time. Now, what will happen if the multiple interrupt will occur all these pins at a time? That's why this can be determined the priority, the urgentness of the interrupt processing, called the priority. So what is the priority? What is the priority of the interrupt?
স্যার কোনটা আগে হবে কোনটা পরে হবে মানে
That is called the
ইম্পর্টেন্স
priority. That is called the priority I am describing. Priority is the interrupt. When the microprocessor receives the multiple interrupt requests simultaneously, it will execute the inter-service routine according to the priority of this diagram. So trap has got the highest priority. It will be given attention first if all these interrupt will occur. Then after finishing, the next priority interrupt signal is RST 7.5. It will be attended. Then after finishing RST 7.5, it will give attention to process RST 6.5 signal and so on. Then at the last, the general interrupt request signals will be processed. So these are called the priority. So INTR has the lowest priority, whereas the trap has the highest priority. In fact, every microprocessor has highest priority. In case of multiple vector interrupt, there is a priority. So priority by priority of the interrupt system means when the multiple interrupt request will occur, which interrupt will be serviced first and which interrupt will be serviced next. So that is called decided by the priority of the signal. So this is the priority of the, but for this interrupt, there is software interrupt, there is no priority because only one software instruction code will be processed at a time. there is no such situation. That means at the same location RST0 and the RST1 will be executed in the sense of in the form of program code. So that's why there is no necessity to assign the priority for the software interrupt, but it is necessary to assign the priority for the hardware interrupt. That's why it is called the hardware interrupt with the priority. Why vector? Because each interrupt service subroutine, the starting address will be calculated according to the given formula. So that's why the name implies the vector interrupt systems. This is called the vector. Now, this is about the theory of the interrupt processing. But there is another techniques, another technique called the masking or non-masking of the non-masking process of the interrupt. What is meant by this? So hardware interrupt, sometimes called hardware interrupt, some of the hardware interrupts are called the vector hardware interrupt, but INTR is called the non-vector because the address is not fixed. The address of the service routine needs to be supplied externally by the device interrupt controller. So that's why the name implies it is called the non-vector hardware interrupt. So every microprocessor has multiple non-vector hardware interrupts, but the 8085 only single, that is INTR, as well as multiple vector hardware interrupt. So 1 and 2 are very important point. What is mean by the masking? First of all, these are the formula already described for this for different vector hardware vector interrupt. The starting address for the ISR is given by this 24 for trap, 2C, 34, 3C. It will be kept in mind that means the length of the interrupt service routine should be such it may not overlap with the service routine of the another vector interrupt. So it should be kept in mind. Otherwise, what will happen? It will create the erroneous operation. Now, what is called the masking? So interrupt process should be enabled. That means not only in general, when the interrupt request signal rather will occur or will initiate, the interrupt will be initiated. Not like that. That's why the global interrupt system should be enabled by the code called EI, Enable Interrupt System. So with the help of execution of the EI, a single byte of code, operation code, 8085 will enable its interrupt system. That means a internal logic. So there is what is the logic part I will describe, interrupt enable. But if it can be disabled by another software code like DI, a single byte of code, even though the interrupt request will occur, the microprocessor will not give attention to those interrupts. So that should be kept in mind. So the interrupt system should be enabled by EI instruction as well as it could be disabled by DI instruction, first of all. So it will disable all the interrupt. But there are some situations when selectively, even though the interrupt system is enabled by the EI instruction, some of the interrupt should be selectively blocked. And this process is called the masking of the interrupt. For example, all these interrupt, among these, except trap, the 4 hardware interrupts can be masked selectively by using another code I am describing. But for RST0 to RST7, those could not be masked because they are not the hardware interrupts. So that is the theory. So how the masking will be done? How the masking operation will be done? With the help of instruction as well as internal control unit called the mux register. First of all, masking could be done by a instruction, a single byte SIM, set interrupt mux. So set interrupt mux means that this immediate opcode, that means the SIM instruction is what? That means the accumulator must hold the relative byte order by 10 bit combination, which interrupt should be masked or which interrupt should be unmasked. Masked means, and what is the process of unmasked? That means D0 corresponds to the M5.5, that is masking 5.5. What is mean? What is the meaning? RST 5.5 signal will be blocked. How? Here it is written 0 means unblocked, that is unmarked, and 1 means marked. User set this bit 1 in the accumulator byte, even though the RST 5.5 interdecoder signal will occur, it will not be processed. So 5.5, the D0 bit signifies the 5 masking bit for the masking of 5.5. D1 bits corresponds to the masking of 6.5. D2 bit corresponds to the masking of the 7.5. D4 is for the another purpose, that is mask set enable. Masking should be done when these bits should be on, that means 1. Otherwise, if this bit is equal to 0 and the user selectively marks any one of these vector interrupt, hardware vector interrupt, again it will not be marked. So mask set enable should be 1. And the D4 corresponds to the masking for RST 7.5 interrupt signal. DF is unknown, undefined, don't care. D6 and the D7s are used for the another application, that is serial data communication. SDE, SOD. This is not related to the interrupt masking operation. So the instruction is SIM. Before issuing the SIM instruction, accumulator should be loaded with this control byte. By this way, any selective interrupt except hardware, INTR, which is unmasked, can be masked. That means this operation can be disabled. But the overall interrupt system may be enabled by EI instruction. That should be kept in mind. Similarly, what are the interrupt systems are masked and unmasked? That can be read out by the another complement instruction RIM, read interrupt marks operation. So that is the byte pattern. And this D7 bits corresponds to the serial input data coming over this line. Basically, there are two lines, SOD and SID, serial input data, serial output data. So these are different operations. For the time being, do not confuse the SID operation and the SOD operation, which the data transfer takes place serially over the two physical pins of 8085. Again, we can show this pinout diagram. If we see the pinout diagram, yes, pin number 4 and the 5, SOD and the SID. Pin number, starting from the pin number 6 to 10, are allocated for the interrupts, echoic signal. So the interrupt systems can be selectively, one or multiple interrupts can be masked or unmasked. So what do you mean by the interrupt system enabling and what do you mean by the interrupt masking? These are different operations. These are the steps of how the interrupt, vector interrupt should be processed. And this is a single table which describes the masking features as well as the ISR address. And the last column indicates the triggering method of different interrupt. What does it mean? That means trap, over the trap, the signal, the logic level either high or 1, we know, according to the concept of the digital electronic. But there is another concept, that is edge. When there is a transition from low to high or high to low, we call the rising edge or the falling edge of the digital signal. So that's why it is written level and edge sensitive. So interrupt request will be acknowledged whenever there is a change in the level, either from 0 to 1 or 1 to 0, as well as the edge, means either negative or the positive edge for the trap signal. For RST 7.5, no level, only positive edge, that means rising edge. So whenever we apply the static signal, it will not be initiated. So rising edge must occur over the RST 7.5 pin. Again, RST 6.5 is called the level sensitive, means the 6.5 vector interrupt will be initiated according to the level sensitive interrupt request signal. That means it must be high. Otherwise, normally it will be low. So for RST 5.5, again it is level sensitive like 6.5. For general interrupt request signal, that is INTR, it will be level sensitive, no case of edge sensitive. That means only this two signal, that is trap and the RST 7.5, are level sensitive, edge sensitive, and only the trap is sensitive to both level and the edge. So that is the interpretation of the last column of the 8085 interrupt system, and these are written here. So what is the masking process and vector interrupt process? These are summarized in the steps which I have just now told. Again, this has been illustrated. And this is a very important diagram, logic diagram of the maskable vector interrupt system. That means you can see this is a equivalent logic diagram which is on chip within the 8085 chip. So these are coming from the external pin, and the mux register is a single bit register like this, so that if it is set to 1 or 0, again it will be blocked, the 3 input AND gate. But INTR has not been passed the request signal to the single bit mux register, the flip flop basically. So with the help of program or software instruction, 1 or 0 can be set to the mux register. So that is the meaning. That means how the SIM interrupts manipulated. Before that, before using the SIM instruction, the accumulator, the A register should be loaded with this byte pattern. Then after this, SIM instruction should be used. So that means the accumulator must hold the byte pattern for masking the interrupt system. Similarly, when we use a RIM instruction, the byte pattern will go to the accumulator automatically. But for SIM instruction, accumulator must be assigned with a particular control byte according to this definition. So these are the sequence how the interrupt can be masked. And there are so many examples. This is the program code. First, the interrupt system shall be enabled by this EI assembly code. Then accumulator should be loaded with the immediate byte move MBI A with a 0A. 0A means according to these definitions, according to this relative byte pattern, 0A means 10. So this will be 0A, that is 10. So that means this should be set to 1, others are 0, and again this should be set to 1, or this should be set to 1. But that has got no meaning. But 0A means prepare the marks to enable RST 7.5, 5.5, and disable 6.5. Why disable? That means if we notice, then this is 1. So 1 means, what is the meaning of 1? And what is the meaning of 0? 0 means unmarked and 1 means marked. That means disable. So that is exactly coming here, disable 6.5. But the 7.5 and the 5.5 are past, enabled. But although the interrupt system is enabled, but by marking that interrupt 6.5 has been disabled. And then the last of, and at the last SIM, that is the set interrupt marks instruction should be used. And these are the description of the triggering level. In general, the interrupt system should be described by this interrupt structure with the logic diagram. See, we can see when the RST 7.5 will occur, basically it's a clock input of the D flip-flop. So the Q will be 1, and that is passed to the internal 3 input AND gate. So if it is unmarked, that means this will be 1, and the third input are coming from the another flip-flop which we will set or reset by DI or EI instruction. So that by this way, the 3 input AND gate, that means 2 input will be 1 logically, and this will be passed directly from the flip-flop connected to the physically the signal RST 7.5. So the AND gate will be high only, but the other will not be. So when the AND gate will be high, automatically the CPU will branch to this vector address 003C for RST 7.5. Same for RST 6.5. The vector address is 0034. And RST 5.5, the vector address is 2C. But for INTR, there is no vector address. And rather, there is a block get restart code from the external device. That means the vector address 16-bit will be supplied by the external device. So that is the interrupt structure. This diagram you must understand what is the meaning of this diagram. For trap, this is vector location, and you can notice there is no masking operation for trap. It is not maskable. Why? Trap has got the highest priority in the vector interrupt system, and it cannot be masked anymore. That means whenever the multiple interrupt will occur, all the time the trap will be serviced. And also, it is not required to enable the interrupt system for the trap. You see the diagram, or disable. Trap is always enabled. What is the significance of that? Means to assign that we give the highest priority to the trap. That means under any situation, the 8085 will attain the ISR for the trap signal. In fact, there is a situation, hardware situation, that means whenever the microprocessor which is excited by the 5-volt DC power supply, and when there is a loss of the power, that means power interruption, what will happen? The voltage will drop down and it will take some time. But there is a logical, that is hardware circuitry which will sense the power failure or the drooping of this power. So it will generate the trap interrupt signal. So as will be serviced, the nature of the service program will be that all important data from the part of the memory will be set to the battery backup RAM. That is another application. So that when the power, when the microprocessor will resume its operation upon next occurrence of the power supply, the data will not be lost. The data will be set aside or will be stored in the battery backup area of a memory, a particular size. There is a memory which are available, which is called the battery backup memory. But normally, that RAM will not be active under normal operation when there is a live power. So that's why every microprocessor provides this facility. That means there must be a power failure interrupt request that is trapped. In case of 8085, trap is that kind of interrupt request signal which has got the highest priority, cannot be masked anymore. So that is the difference why the trap is not unmaskable. These are written here also. These are written here. So this is all about the interrupt processing. But That is the application of the interrupt program that will be discussed in the next class. That means whenever we'll start the interfacing of the external hardware. And that is the important part. But this is the theory of the interrupt, vector interrupt, how it can be masked, non-vector interrupt, so its classification. These are all described right now. Now again we are going to that important area of programming. So that means time delay generation. So with the help of program or software, a counter and a time delay can be generated. We know in digital electronics, do you know, I think you maybe have what is counter. Basically, it will count the number of event occurrence of the timing event, and the counter programming is required. Counter hardware block, it is basically a flip register. That is, counter is maybe a synchronous, asynchronous, you know, according to your knowledge of the digital electronics. But with the help of microprocessor, the counter can be implemented using software program. So what is the role of the counter? That is in the programming part, how the number of pulses will occur as a timing event as an interrupt signal, which is connected to the RST 7.5. Then we can develop an ISR, interrupt service routine, to count up the number of occurrence, as well as with the help of the number of occurrence as well as the periodicity of this occurrence, we can measure the time period as well as the frequency. So time delay has got the similar like application, time delay. How we generate a fixed amount of the time delay in millisecond or second by using the software code. So what will be the implementation of generating time delay? So look at this software code, MBIC FF, the highest value of the single byte register. Then DCRC, the content of the C is decremented by 1. Then JNZ, until the C is decremented to 0, it will branch here, decremented to C, and will go on. Now, every microprocessor assembly language, according to the datasheet, there is a T states according to the machine cycle, which are written. 7 T states. For this instruction, 4 T states. For J and J, we will find the two alternate T states. One is 10, one is 7. What is the meaning? That means when the 0 flag is set, it will come out from the loop. Otherwise, if the 0 flag is reset, it will branch to the DCR instruction. That means upon trueness or falseness, the T states will be different. When 0 flag is set, 10 T states will be consumed to execute the instruction. But when 0 flag is reset, only 7 T states will be consumed. But how we calculate? We have to calculate. So what is the amount of the total T states under looping operations if the clock frequency of the system is 2 megahertz? So one clock period is 1 by 2, that is 0.5 microsecond. Now we can calculate how much amount of the time will be consumed according to the T-stage calculation for each and every instruction. So MBI will consume 7 T-stages, so the time of operation is 3.5 microseconds. So time delay for decrementations of 8 milliseconds. So equivalent decimal of the hexadecimal count loaded in the delay registers, that is whether it will be FF, that will be determined by using the formula. So how much will be the total time after repeated loop operations? So we can easily calculate in this manner, where TLA is the time to execute the loop instruction, TL is the how much will be the value of the loop, 3 T states in the clock period. This is the illustration. In general, the formula will be like that. Formula is like that for this type of program code. X into What is the total T states? 7, 4 and say 10. 10 means we assume the false, that is 7, 4 and 7. So 7 and 7, 14 plus 18. So 18 multiplied by the x minus 1 plus 10 number of T states will be executed, where x is the amount of the or byte loaded to the C register, that is unknown. So the total T states for executing this program code will be x multiplied by the 7 plus 7 into 4, that is 14 plus 4, 18 plus 10. So x into 18 plus 10, that will be multiplied by 0.5 microsecond, that will be time delay. Now, writing this equation, how much time will be required? We can form an equation, and from which we can solve what will be the single byte opcode to generate that amount of the time delay. But the time delay is limited for a single byte register. It must be kept in mind. But if we require the higher amount of the time delay, then we must use the 16-bit register like BC pair. So time delay for one loop is 109 milliseconds, which is much more higher. Again, more time delay can be generated by nested loop statement like this. So 24-bit, that is within loop, we can use, that is BC register, as well as BC register is 38, and multiplied by the another, within the nesting operation, another byte register has been used. So that more higher time we can, so that how we can generate the time delay in millisecond or in second. And that is the flow chart, how we generate the time delay. Do you have any confusion? How the T states of the instruction will help you to calculate the necessary time delay to be generated. This is a very important part for time delay generation. So with the help of these things, the microprocessor can generate the time delay, only time delay. But this time delay, during this time delay, what will happen? Because the looping will go on. Only the looping will go on. No other tasks will be done, because multiple times the microprocessor will branch with this help of instruction. There is also another type of instruction called no operation, knob. It will do nothing. We can also use the knob, but knob will give you a limited T states according to the data sheet. That is not general, but whenever it is required to generate the time delay operation, we must write this kind of program. This is the nested time delay flow chart. So this is a counter program now. Counter time delay is basically, this is a applications of the counter for generating the time delay. What type of counter? It is down counter. Generally, the up counter program, up counter feature is not used. Down counter. DCRC means counting down by one. But we could write INRC. In that case, it will be up counter. Then we have to compare whether the counter has reached to the FF value. The same thing will be done by using the up counting program. But in general, the time delay program uses the down counting method. So basically, the application of the counter is will exist in the time delay generation. The same thing could be done in digital electronics by using a multiple stage flip flop, ripple counter or synchronous counter, whatever may be. So now we can understand that means, and what is the advantage of using the software counter? That means in case of a counter design using the digital logic gates or sequential logic circuit, the variations of the clock frequency, accuracy of the clock frequency may yield the inaccuracy of the time delay generation. But here, in the case of microprocessor based time delay generation, the error will be very, very small. Even there is no error because the microprocessor timing signal is initiated by crystal clock of a particular value, clocking signal. What is the operating clock frequency? What is the 8085 clock frequency? 3.077 megahertz. So in the time delay generation using the 8085, the basic clock frequency will be 3.077 megahertz. So 1 by T will be 1 by 3.077 megahertz. It's so small microsecond. So that is the philosophy how we can generate the time delay. Did you follow the logic of time delay generations with the help of program? What is the formula? Hello, did you follow the logic behind the time delay generation using assembly language program, 8085 assembly language program? Later on, we can use the time delay generation program for generating the square wave through the I/O port. We'll see. So the time delay generation program has a versatile application in microprocessor, or any type nature of the waveform, that is periodic waveform, can be produced with the help of time delay generation. Square wave, sine wave, triangular wave, everything. Square wave will be the easier, that is rectangular square wave. But it requires the interfacing of the I/O device or programmable peripheral device. So this is we have just illustrated the today the interrupt systems of 8085. And the timing diagram of the interrupt systems will be how much will be what? So you must understand the timing diagram of the different types of the instructions, like DAA, decimal adjust after addition. What will happen in the opcode fetch cycle, because it is a single byte opcode. So what will happen in the different T states? These are illustrated with a different waveform coming over the illustrated with the different lines. So that is called the timing diagram. What is the timing diagram of XTHL? This is a big operation which requires a multiple machine cycles. Each machine cycle will consume some of the T states. Carefully, or it will. And what is the timing operation of what is the operation of the branching instruction? What is the timing diagram of the SPHL? So these are very important. Similarly, because I have described, that is the meaning of the memory read-write, IO read-write, opcode fetch cycle with the help of this diagram. What will flow? According to the left part is the data flow diagram, another is the timing diagram, and this is the interrupt acknowledge cycle. So what will happen once the interrupt request signal will occur? Look at this diagram. Interrupt acknowledge cycle for RST instruction, restart instruction, restart 0 to restart 7. If this will be executed, then only single byte opcode. And you can see the speciality. That means for restart instruction, what is the opcode fetch instruction? M1 cycle corresponds to the opcode fetch instruction. So that is 4 T steps. But the special case is that the first machine cycle has got the 6 number of the T states. Subsequent machine cycles M2, M3 are the 3 T states. So that is the typical timing operations of the restart interrupt process. That is interrupt acknowledge cycle for the RST instruction. This is special. This is a special thing, and these are described. Interrupt acknowledge cycle for the ISR calling, because ISR will be called. So that's why it is similar like call instruction, but under the actions of the INTR. So this will be the picture. How many machine cycles will be executed? Because call is a 3-byte instruction. So M1, M2, M3 will be required. At the same time, why M2, M3? Because the M2, M3 are the 16-bit operand. Then M4, M5 will occur also, or required. Why? Because the timing, that is the signal will be generated, that is the INTA bar. So timing diagram of the INTA bar for occurrence of the INTA and interrupt request, machine cycle and execution of call instruction. So first the INTA bar will be generated by active low logic when the INTR will occur, because this is timing diagram on the action of the INTR. Then again at M2 and the M3 machine cycles, two further pulse transition will occur over the INTA. Then it will be inactive. Why write bar is required? Because it is a calling operations. So calling operation require the writing the updation of the stack pointer with a stack memory. That means to the stack pointer or the program counter should be set to the stack memory. That's why it's a memory write operation. That's why 2 times you can see the transitions of the write bar signal. So this is very conceptual things. That's why the 2 machine cycles are required, M4 and the M5, for initiating the write the content of the return address to the stack memory. And these are the intermediate things. So this is very important. There is another type of timing diagram, timing cycle, bus idle cycle. What is that? Under no operations or instruction of the DAD instruction, these are timing diagram of the DAD instruction. But why? There are few situations where the machine cycles are neither read or nor write. So both read and the write bar will be inactive, but it is not like that. So this is called the bus idle machine cycles, which will occur where when the halt instruction will be executed. So there is another timing diagram of the halt instruction, but the halt instruction machine cycle timing diagram is called the bus idle machine cycles, which are described here. So that is the meaning of the bus idle machine cycle. This is the thing. Both write bar and the read bar are at inactive states, inactive logic. So what is the operations of the bus idle machine cycles? That is described here. But for interrupt processing, this is the interrupt acknowledge machine cycles. But in case of a RST operation, restart operation, only the interrupt acknowledge machine cycles will be generated, but it is not required for the interrupt signal. It is required, that means yes, microprocessor is processing the vector address signal. So that's why the INTA will be generated. That means negative logic, active low. So these are restart instruction for RST0 to the RST7. As well as it is similar like for hardware vector interrupt address, that is RST 5.5 trap and the RST up to RST 7.5. This timing diagram. Because the code is restart, it is equivalent to the RST 5.5, but you cannot use the RST 5.5 software code. There is no as such opcode. You have only RST 0 to RST 7 opcode. So that is the difference. So many concepts are very much applicable in case of processing the vector interrupt address. You must understand step by step. Another thing is that wait states. What is mean by the wait states? Generally, the microprocessor will transfer the data to and from the IO or the memory in sequence of opcode fetch cycles and the memory read bar, IO read bar, or memory write bar, IO write bar machine cycles for data transfer. But sometimes the memory may be slower at the IO devices. So that's why there is a ready input signal to the microprocessor. You can notice. If the ready input is permanently tied to the high logic, so the microprocessor will not initiate any wait state. But in general, input signal is generated with the hardware logic signal. What is that logic signal? This is the logic signal. Or better, we can this signal. You can see the typical logic signals or logic circuit for the ready generated. So these are clock out, these are 5-volt, master slave D flip flop. The output of the second stage as slave D flip flop is connected to the inverter gate, and that will go to the microprocessor's ready input signal. Now we can see this clock out signal is coming from the microprocessor clock signal. So what will happen? You can see there will be a delay by one clock signal. According to this diagram, logic circuit to control ready signal input. How much will be the delay? That is 2 clock signals. After 2 clock signals, we can see the ready signal. In fact, the ready for the that is according to the logical circuit, the ready signal will show the transitions at the middle of the first T states, and it will be there for the middle of the, that is after the finishing of the second T states. So that is the timing operation. That is the time delay generated by this signal. So ready is not high always. Ready will show a pulse transition with a negative logic of this amount, and that will occur relative to the T states, fixed T states. So when the microprocessor will see at the second T state, that is ready signal is low, what it will do? It will insert a wait state. That means a dummy clock state will be passed. Nothing will progress. So you can see over the other timing and the control signal address bar data bar, all the signal will stay in the last state. And after completing the wait state, it will normally progress over the T4 and the T3 states. So that is controlled by the ready input. Why the microprocessor is delayed by one single T state? Because by the meanwhile, that means the external memory and the IO device get enough time to receive the data according to the data transfer operation. So that is the application, how the ready input signal will be controlled by the external logic circuit. These are separate the microprocessor circuit. So this is another applications of the ready input signal with using the monoshot, that is monostable multivibrator. Here, this delay can be controlled by the value of the timing element R and C value, because according to the formula of the monostable multivibrator, where T is equal to, depending on the circuit, this delay time is equal to some fractions of the Rn into C. Maybe for this circuit it will be 1.44 into R into C. That is the typical value of the monostable multivibrator using 74121 integrated circuit. So that using the setting the value of the R and C, we can generate a variable wait state. What will happen? If the ready input is again low up to this mark, another T states will be produced, inserted, or will follow. So multiple T states can be generated by the microprocessor with the help of this circuit. So that is the role of the how the synchronization between the microprocessor and the memory and the IO device can be controlled by the ready signal controller. So you must understand the concept of ready input. And what I was telling, that is a halt state. Wait state I have discussed. What about the halt state? It is to some extent after executions of the HLT instruction, that is halt instruction, microprocessor will stay in an infinite bar idle cycle. Infinite bar cycle means it will neither fade up course nor do anything. All the timing signal will be frozen. This is called the bar idle. Address and the data bus will go to the high impedance states under the bar idle machine cycles. So that is the physical significance when the bar idle. What is the bar cycle? That is upon execution of the halt instruction, microprocessor will stop fetching opcode and doing anything, but rather all the signal as well as the timing and the control and the address data bus will go into the high impedance states called bus idle machine cycles. So that is the significance of the bus idle machine cycle, There is also another typical situation like hold state, but that is a very complicated. This is a temporary halt state or bus idle state. It can, but the normal operation can be resumed upon withdrawing the hold signal, because in the 8085 there is a two input signal. One is a hold incoming signal, another is a hold acknowledge HLDA outgoing signal. But whenever the multiprocessor are connected, that means two 8085 are connected in between, then these two signals are required. That is hold and hold acknowledge. That is different. So these are the very conceptual things for the wait state generation, why it is required, and the bar idle machine cycles. So did you understand? You have to go through these notes.
স্যার এগুলো সবগুলো নোট কি ওই যে একবারে যে পাঠিয়েছিলেন ওখানেই আছে?
আরো আপডেট